Welcome to Revise for Physics, the place where you revise for physics.
Hello. In my last video I looked at the detection of radioactivity. The main topic was looking at background radiation to give you an idea of what causes background radiation, where it comes from, what it is. And I also talked briefly about how you can detect alpha particles, beta particles and gamma rays. Today I'm going to go into a little bit more detail about the detection of these alpha, beta and gamma particles. To understand how they're detected, you really need to understand what they are and the different properties, so as you can distinguish between them and you can identify which one is which. And I'm also going to look at some of the supplementary data or supplementary information that you need to know, as listed here for these specification points. So firstly we're going to look at the nature of the different particles, alpha, beta and gamma. By nature that means what it is, what it's made from. The alpha particle is a helium nucleus. It's very heavy compared to the others and therefore carries a lot of energy, which makes it highly ionizing. Because it's so big, however, it's not able to penetrate very far. Beta, on the other hand, is a high energy electron. Because it's an electron, it has some mass, and because it has mass and is charged, it's moderately ionizing and it's moderately penetrating, which means it's able to go through some things. Finally, we have the gamma particle, which is ionizing but not as ionizing as the other two, and is able to penetrate pretty much anything, which means it can go for hundreds, millions, thousands of millions of kilometers. The alpha particle is unable to pass through the hand. That shows that it is not able to penetrate things very well. It's stopped by flesh, stopped by paper. Beta particles, on the other hand, are going to be reduced by the hand, but not a lot. They are, however, stopped by aluminium, and it can be relatively thin aluminium, so they're unable to penetrate the aluminium. Gamma particles, on the other hand, are able to penetrate hands, flesh, paper, and aluminium. They might be partially reduced by the hand and by the aluminium, but it is then absorbed by lead, and lead is a very good absorber of radiation. I'd now like to talk about the Geiger counter. The Geiger counter is what we use to detect radiation, and it's a device that's made up of two parts. It's made up of a Geiger-Müller tube, which creates a small electrical signal when radiation passes through it, and a counter, which is what counts those electrical signals from the Geiger-Müller tube. Now this is an animation designed to show you how the Geiger counter works. And it works really well. The wooden block in front of the Geiger counter is designed to hold a source. A source is just a source of radiation. The plastic looking tube is the actual Geiger-Müller tube, and then that's connected via the leads to the Geiger counter, and you'll be able to see that counting the radiation. We're going to start off by measuring background radiation, and that's what we talked about in the last video. It's the radiation that's around us all of the time. And then once we've got an idea of the value for background radiation, we'll go on and we'll measure the radiation from a couple of different sources. Here you've got the background radiation being counted by the Geiger counter, and it reaches a count of 4 counts in 10 seconds. And now I'm going to move on to americium-241, which is a radioactive isotope. So here I've got the americium-241. I'm going to time it for 10 seconds and see what the count is. And that's what you should do, is time over a long period of time, and then you get a nice reliable average. Obviously you might want to time for more than 10 seconds in reality, but 10 seconds in this case is perfect. So I've first timed it for 10 seconds without anything in the way, and now I've put a piece of paper in front of it, and you can see that the count after 10 seconds is lower here. Now with a piece of card in the way, After 10 seconds, the count is almost as low as it was just with background radiation. And that shows that the card is absorbing the radiation. Now if I put a thin sheet of aluminium, the count drops right down to background radiation. So if we put this in a table, the americium just by itself had a count of 17. With paper, that dropped to a count of 11, with card it dropped to 9, and with aluminium it dropped to 4. Now as background radiation was 4 counts in 10 seconds, that shows that with the aluminium in place, that the count is reduced to background radiation. So if all the radiation is absorbed by aluminium, that must mean that the radiation is alpha particles. So that means that the americium is an alpha particle emitter. Incidentally, if we look at it at a distance of 10 centimeters without any sort of shield, you can see that the radiation doesn't increase as much, and that indicates that alpha particles don't go very far in air. Next up, we're going to look at another source, which is strontium-90, and it'd be nice to try and determine what sort of radiation comes from strontium using the same methods. Repeating the same methods, we'll time for 10 seconds, and then we'll try with different objects in the way to see what absorbs the radiation. Now, with nothing in the way, we get a count of around about 700 counts in 10 seconds. At a distance of 10 centimeters, you can see that it drops, and that's partly down to the fact that the radiation would have to be spreading out. When we put it back to 1 centimeters with paper in the way, the count doesn't drop at all. It stays around about 700 counts. So that would indicate that we don't have alpha particles coming off. Now with a thin sheet of aluminium, the count drops to 543, which is a significant drop. And then with thick aluminium in the way, we get a drop down to a count of 5, which is very close to background radiation. Now before I put that in a table, I'd like to look at another source, and we'll try and distinguish the different types of radiation that come from the two sources, the strontium and this luminous watch. Now you're wondering what a watch has to do with radiation. I'd urge you to look up the story of the luminous watches, because it's a tragic story, and these old luminous watches are incredibly dangerous. When they were first produced, the luminosity, rather than using some fancy paint, was using a paint that had radioactive minerals in it, and it was so radioactive that it was giving off light, that it was glowing in the dark. Now if you had one of these watches, it would still be too dangerous to wear. However, this is just an animation. I'm not about to get cancer from a watch, and so we'll carry on. Now again, repeating the process, starting off with a watch at 1 centimeter away without anything in between the watch and the Geiger counter, you can see the count is flying up. It's giving off a lot of radiation. If I put a barrier of paper in between the watch and the Geiger counter, it's still going up by quite a lot. But if I add aluminium, and I'm going to use thick aluminium because that'll give a better indication as to whether it's beta or not, you can see that the count goes up very, very steadily. But the count is still going up a little bit. So using lead, we can distinguish whether some of that radiation is gamma. Now because lead reduces it more than aluminium does, that shows us that we do have some gamma rays coming off. Putting it all in a table, I'm going to put the strontium in the table, and I'm going to put the old watch in the table. Now you can see that there's a decrease with the strontium when I introduce the card. Now that would indicate that there are some alpha particles being given off. The aluminium reduces it by a small amount, and thick aluminium reduces it by a lot. Now that would be down to the fact that there are energetic beta particles. The more energy the particles have, the more they can go through lead or aluminium or paper. And with the old watch, obviously I had to test it with lead to see what was the source or the barrier that I would need to get it down to background count. So here are the final results, and this is where the science comes in. You can see that the strontium is reduced by paper, which would indicate that there are some alpha particles being emitted by the strontium. The strontium is then reduced almost to background count, or to background count by thick aluminium, which would indicate the presence of beta particles. The old watch was reduced partly by paper, which would indicate the presence of some alpha particles, and it's then reduced almost completely by thick aluminium, which would indicate that the majority of the particles are beta particles, and then there's a small further reduction down to the background count by lead. Now that indicates that there are some gamma particles being produced by the old luminous watch. Now finally I'm going to do the same thing again with thorium oxide. I'm not going to go through the results this time, I'm going to let you try and work it out by yourselves, but I'll talk you through the steps. So we start off again, very close with no barrier in the way, and we can see what the count is after 10 seconds. Then again we try again, but with card in the way. You could use card or you could use paper, and you can see how the count changes here. The count is on the little counter, and you can see when the timer gets to 10 seconds. Now we're going to change it to thin aluminium, and you can see how that changes the count again. Has the count been reduced? Is it the same? That's the thought process that you should be going through. You should be trying to work out if it's been reduced by aluminium, and if it has, then that would indicate the presence of beta particles. Now I've got thick aluminium. Has that reduced it even more? If that's reducing it, remember, what will go through aluminium, thick aluminium? What won't go through thick aluminium? Now I've put lead in the way. Now the lead, does that reduce it? Is there still something going through lead? Now in this case, there is still something going through lead, and the only thing that could be going through lead would be very strong gamma rays. If I try with thicker lead, some of it is still going through, which would indicate that these gamma rays are very strong. Right, so just to recover, we have done the characteristics of the 3 different kinds of emission. So you should be able to identify alpha, beta and gamma emissions from their nature. Their nature, that's what they are. So the alpha is a helium nucleus, the beta is a high energy electron, and the gamma is an electromagnetic wave. Their relative ionizing effects, alpha being the most ionizing, gamma being the least. Their relative penetrating abilities, and that's where they're the opposite, where gamma is the most penetrating and alpha the least. And then you should be able to use that information to be able to detect and distinguish, and that links back then into these points on the detection of radioactivity. So to move on to some of the supplementary points, deflection in an electric field. So how they deflect in an electric field is due to their charges. Now if you recall, the beta particle that I've drawn here in black is a negative electron. So being an electron, it will be attracted towards the positive in an electric field. Now electric fields, as I've drawn here, go from positive to negative. The field is defined by the direction that a positive charge would move, okay? So in perfectly straight lines, not quite like I've drawn here. Now the gamma, which I've got in red, will be unaffected by the electric field because it's neutral, so it passes through undeflected. And the alpha particle then, because that is positive, will be attracted down towards the negative side. Moving onwards to the deflection in a magnetic field, the deflection is down to Fleming's left-hand rule. So if you don't know what this is going to confuse you a little bit, but you should be able to distinguish the direction of a magnetic field from these symbols. With this symbol means going into the page or into the screen, and a dot, okay, if I were to just have a dot, means coming out of the page, and it's supposed to be like an arrowhead. So if you get your left hand and point it at the screen, okay, if you point your index finger into the screen, then that says which direction the magnetic field is. Your index finger describes the magnetic field. Now the alpha particle is positive, so if it's moving in this direction, the current is towards the right hand side of the screen, so in line with the motion. And there's an upward force on the particle that's dictated by the thumb, okay, the thrust of the motion is upwards, and so that will cause the alpha particle to curve upwards. Now beta particles, being negative, if they're moving in this direction from left to right, then that's as if positive current is moving in the opposite direction. So you'll have to turn your hand the other way. So your thumb is now pointing down, your second finger is pointing to the left, even though the electron is moving to the right, and the field is into the page still, okay, the field here. Now the motion, the thumb, the force is acting downwards, and so that will deflect the beta particle downwards. The next specification point talks about the uses and practical applications. So I've drawn one here. Okay, now this is a paper or aluminium mill. Now the beta source and the detector is here. Now paper is will partially absorb beta particles. Now that means that the detector will detect less if there's thick paper, although this also obviously works for aluminium, as you've seen from the earlier part of the video. So you need some sort of feedback from the detector to the roller, whereby if the detector, if this is aluminium, if the detector is not detecting enough, then that means that the aluminium here is thick and the roller will need to press harder. Okay, so that will roll the aluminium thinner. There's also a lot of use of radioactive particles in medicine, for example in tracers. Now tracers, for example technetium and other radioactive isotopes, are used as tracers, and what that means is they're ingested, okay, maybe they're swallowed, and then they travel around your body and they can be detected using something very similar to a Geiger counter. So if, say for example, you had some sort of cancer that was detected by a blood test, doctors would then want to know where that cancer is, and the best way to do that might be using a tracer that contains a form of radioactive sugar, which sounds a little bit scary, but it's got a very short half-life, so it releases its radiation very quickly and then will leave you unaffected afterwards. So if there's a lot of radiation in this part of your body, that means that the sugar is going to here, and that could be indicative of a lot of cellular growth, which would need a lot of that sugar. And so you'd get radiation being given off here, which could be detected, and then you'd know to look in this part of the body a little bit better. But as you should be aware, due to the ionizing properties of radiation, they can also kill cells. Now that means that a different sort of radiation, okay, could be used to kill the cells here, and that would be called radiotherapy, okay, using radioactivity for therapy on cancer. Okay, and you can also use radioactive isotopes for radio dating. Okay, carbon dating is a type of this, and I'll talk about that a little bit more in my video on half-life, so as we don't overdo it for this video. So hopefully you found this a useful video, and I would recommend, if you didn't understand something from the video, that you go back and you look over it again, that you listen to it again, and maybe hopefully then you'll understand that particular section. If you spot any mistakes, feel free to comment and I'll see what I can do to try and fix the video. Thank you very much, and thank you for watching.